Alright everybody, good to see you guys here again, and this is the second part of the video lesson that supports this booklet, Applications of Sinusoidal Functions. We've already covered the tsunami, the Ferris wheel, and calendars. So let's have a look at, Ferris wheel and nails and tires. Let's have a look at calendars today, because this is, I think, the most complex of all the jobs that you wind up doing. And it involves a little bit of sci-fi and all that kind of stuff too. So it's interesting, but it requires skill. And let's see how things go. So calendars were established long ago. I mean, before there were malls that you could go shopping on Christmas Day to get calendars for. But long ago, to help people figure out when to plant crops, when to go fishing, when to do whatever. Right? You needed to have certain times of the year where things were optimal in order to get the best results. So you have early calendars like Stonehenge, and even some people say that the pyramids acted as calendars as a way to figure out what time of the year it was, because people didn't always know when the solstice was. You couldn't always figure it out unless you had people sticking around and paying attention to those things. But if they're paying attention to those things, that means they're not farming or fishing or fighting wars or anything like that. It's usually the priestly classes that were tasked with that kind of observation. So in a calendar, you'll have the hours of sunlight, or if we take a look at the graph of hours of daylight relative to time of year. Okay, so at day 0, we'll say, this is not our New Year's, but let's say day 0, this would be like the spring equinox, which for us is like March 21st, 22nd, depending on leap years and all that. And the hours of sunlight increase to get to the top, which is the summer solstice, about a month away, which is June 21st, around there. And that's the longest day of the year, the solstice. So sol means stop, sol means sun, and stis means stop, and so that's where the sun stops in the sky. It doesn't go up any further, because up to that point the sun gets higher and higher in the sky. It stops, and then it starts to drop lower and lower and lower in the sky at at sunsets or sunrises, until we get to the fall equinox. Equinox, equi means equal, nox means night. So sol means day. So sun stops, and equal night. So equal day, equal night, and the fall equinox happens in September 21st, around there. It drops down to the winter solstice, which is for us December 22nd, 21st, something like that. And then it goes back up and gets back to the spring equinox. Now for us, we have our New Year. Our New Year happens right after the winter solstice, about a week after the winter solstice. So this is where we put our New Year, right there. But that makes no sense why we have it on January 1st. Like, why would we even set up a calendar like that? It's very rudimentary, and it's an interesting study. If you just Google or YouTube, origin of calendars, you'll find a lot of information. A lot of it goes back to Roman times. The calendar that we have is different partially from the calendar that, so they call it the Gregorian calendar. It was different than the Eastern Orthodox calendar, and even to this day, Christmas in Russia is different than Christmas in Western Europe and across the world. And it has to do with the way their calendars were set up. So why set it up one way versus another? It would make sense to set up our calendar to start the new year at, say, the spring equinox, or at the winter solstice, or at one of these nodes here that's very easy to point out, the summer solstice. And for many pagan religions, that's how they set it up. Astrology sets its calendar up for the spring equinox. Kind of makes sense a little bit. But there are other things that put it on different spots on the calendar, and we here in the West put it here. Absolutely weird place to put it. Why would we start our own counting system at that point? It makes no sense. So the reasons why that is, and a lot of other history can be explored. A lot of it comes from ancient Rome, because guess what? We still feel effects of ancient Rome. It's not gone away, and so this is our graph of how things work. So what I want to do today is I want to create an equation that talks about how to figure out the hours of sunlight on a particular planet somewhere off, wherever, and the inhabitants of that planet decide to make the calendar start somewhere ridiculous like where we have ours, right? For no really good reason why we put it where we do. So let's create an equation. We'll do it for planet Earth, and then we'll do it for planet a bunch of other ones and see what we can create. So obviously, right, we're going to have the hours of sunlight. You'll have a top and the bottom. You'll have the length of the year. You'll have a phase shift, right? Well, for us it would be a phase shift from a negative cosine graph, because we start the cycle there and we'll phase shift it a little bit to the right. Is that right? Yeah, phase shifted to the right. So how do those equations work and what do they look like? Well, let's have a look at a particular example. Okay, so I've got a situation here that's similar to what we see on Earth. I said, let's create an equation for the hours of sunlight on Earth at a spot where the winter solstice has 7 hours of sunlight. Okay, so here's kind of the drawing. Remember, on Earth, our winter solstice, we'll say it happens on December 22nd. Okay, so we'll put here, this is December 22nd. So December 22nd is how many days away from January 1st? Well, so 23rd, 24th, 25th, 26th, 27th, 28th, 29th, 30th, 31st. What's that? 9 days. So 10 days to January 1st. So our h value is equal to negative 10. Right? It's 10 days to the... Actually, it's positive 10, right? Because it's 10 days to the left. Right, I moved it. Actually, okay, I see what you're saying. So negative 10 right there. Okay. Right, negative 10. I have my wife in the other room distracting me. So yeah, negative 10 is 10 days before the solstice, before January 1st. So the solstice is early, right? Technically it should be moved over, or we should start our year there. Okay, so it's a negative cosine graph, right? So hours of daylight, h hours at the different time of day, is equal to negative a cos b, the day minus 11, minus 10 plus k. The opposite, right? So when I have minus 10 days, I plug that in, boom, it's going to be plus 10, right? We did the opposite of our h value, so plus 10, and then I got to figure out a, b, h, and k. So one of the ways to figure that out is, okay, well, if we have 7 hours of sunlight at the solstice, at the winter solstice, that's a 5-hour difference, right, between 12 and 7. So at the summer solstice, we're going to have the same thing. We're going to add 5 hours. So 12 plus 7 is 19 hours of sunlight on the summer solstice. So we have an amplitude, a difference here of 5. And remember, that's how we calculate our a value, right? Top minus bottom, top minus bottom divided by 2. Is that right? Yeah. I can't even do my own math. 17. Oh. Okay, so 7 and 17. Okay, and so our b value, right? Our b value is 360 divided by our period, which is 365. So we're just going to leave that as a fraction. Or you can calculate the decimal for it right now, right? It's 360 degrees divided by the period, so 365, yada yada like that. Our d is our variable, so day value somewhere in terms of where we are from January 1st. So if January 1st is day 0, then it's 10 days after the solstice. And our k value, well, that's just our baseline, right? Which our baseline is 12. So boom, that's always going to be a 12. And so we can create our equations fairly easy, right? This is going to be negative 5 cos 360 360 over 365 d plus 10 plus 12. Okay, so part of your job is to create the equations for that. Now, depending on where on the Earth the hours of sunlight that you get at different spots differs, right? At the equator, you don't fluctuate a lot. If you go up to the Arctic Circle, you fluctuate quite a bit. In fact, you'll have negative values. You'll have, times where you have no sunlight, and then you have times when you have all sunlight. And so you'll have numbers that are above 24 and below 0. And those are just theoretical values that you need in order to create your wave function. Okay, so let's have a look at some sci-fi calendars and see what we get there. Okay, so here's a sci-fi planet. Okay, it has at their summer solstice they have 15 hours, and we'll just assume it's 24 hours because you can apportion your day however you like into 24 hours. But we'll say it's got 15 hours of sun on the summer solstice. The planet takes 240 days to make a year. And they start their new year 5 days after the spring equinox. So let's have a look at what that might be. Okay, so here's a quick look at how they would measure out their hours of daylight. 12 hours is the middle because we're working on 24 hours. They go up to 15 at the summer solstice, and they go down to 9, right? Because 12 plus 3 is 15, so 12 minus 3 is 9. So that's kind of implied in the numbers. You have to remember to sort those out. And it's starting 5 days before, they start the calendar 5 days after the spring equinox. So here's spring equinox at t minus 5. 5 days, they get to the start of their calendar. They're still going up, and then they go down. And they come back up at day 235. They're back at their spring equinox, and they got 5 more days to get to their new year. Right. So there's the shape of their graph. It's a positive sine graph. So hours of daylight is going to be equal to a sine b d plus h plus k. And we can figure out a few things. A value, the radius, right, is going to be 3. Your B value is going to be 360 degrees divided by 240. So we can simplify that. 6, so that's going to be 6 over, no, we can divide by 12, so 3 over 2. Yeah, 3 over 2. Okay, and your H value, well, I'm minus 5, right? So so then I'm going to make that a plus 5, right? Because I'm going to add 5 days from their equinox. It's the negative of the number that you see there. And then your K value is always going to be 12. Okay, so those are the values, and I just created my equation. The hours of daylight is equal to 3 sine 3 over 2 d plus 5, right? Because I have to add 5 to that, and then plus 12. Cool. Let's see if I can make that a little bit better. Cool. Okay, and so it's just, setting up what the graph might look like over here, and taking the parts that you need and calculating your A, B, H, and K. Hopefully by now, if you've been keeping up, the ability to calculate A, B, H, and K can become quite obvious because there's formulas that go with that. Plus, there's also very quick ways to tell. And the hardest part I find, and you even saw me do it a couple times, is remembering, okay, well, my H value is the negative of that particular point, right? So I've got to make sure that I include that as the negative, where I make sure I write that in there as the negative of how it starts. If it starts 5 days after, right, then I've got a plus 5, and that would be a minus 5 down there. So just keep in mind those details. And of course, I get you to think of things like, okay, what's the time interval? So I'll get you to say, okay, well, let's say the fishing is best when the daylight is, is less than 10 hours. So you go to 10 hours over here, you stick in a 10, and you'd have to calculate out D. So I'll go through a quick calculation that sorts that out, because the substitution is a little bit tricky, and then that'll be it for the lesson. So let's have a look and figure out how to do that. Alright, so I wanted to find that time interval where the hours of daylight are less than 10 hours, 10 hours or less, right? So if I'm thinking about my graph, right, it kind of goes up like that and down. The bottom is 9, so 10 is just a little bit above that. And I got this little time period, right? How long is that fishing season, or whatever it is that you need to figure out? Okay, so it's just math. Let's go forth and calculate for D. It's a little bit tough because you have to sub out this entire middle part for a variable, and that's where we really start. Okay, so I need to sub out my my angle expression for just a simple angle expression, and then I want to make the hours equal to 10. Okay, so I got to solve for big X, and let's go through that. Okay, don't forget to keep your sign positive, so 2/3 is 0.6, and then negative, but we keep it positive for our calculator, and I get a reference angle of 42. But then I got to go to the cast rule and say, okay, well, let's have a look at the cast rule. Where is sign negative? Okay, so sign is negative in the T and C zone, so I got to add to 180, and I also got to subtract from 360, right? So these are these guys here, and these are what I get as my my principal angles. But remember, that's just x, so I guess these should really be x's, not thetas, but yeah, same idea, big X1 and big X2. And don't forget, they're equal to this, right? So each of them is equal to 3/2 d plus 5, like that. That's what they're equal to. So how do I solve for d, right? How do I wind up doing that? So I'm going to erase this, and we'll solve for d, and then we'll do our delta t. Okay? Okay, so if you recall, right, our big X is equal to 3/2 d plus 5, so our angles, here are our angles, and this is what they're equal to. So I got to solve for d. So first off, I got to get rid of a divide by 2, so I have to times by 2 to both sides. So I'm going to times that by 2. That's what, 444 is equal to 3 times d plus 5. Now I have to divide by 3. Okay, so 444 divided by 3 is 148. So I have 148, right? I'll divide that by 3 over there. 148, and these guys cancel, is equal to d plus 5. So I got a minus 5. So day 143. That's day 1. That's the first fishing day, or whatever, on their calendar. And we do the same thing for the last fishing day, so we can figure out how long the fishing season is, etc. Okay, so let's see if you can do that, see if you can get it before I do. Alright, that's what I got. So 143 is the start of the fishing season, and 207 is the end of the fishing season, say. And so how long is the fishing season on their planet at that particular point? Well, we just have to find the delta D. What's the difference in days? How long does it take? So on planet Alpha, they've got 64 of their days for fishing season, say. Okay, so these are the types of calculations you wind up doing at the end of the booklet, and this really takes us to the very end of that particular booklet. Next week we're going to start something called Trig Identities, and that is like what I call math yoga. It's one of my most challenging parts of the course, and we won't get through all of it because we just won't have enough time because we're going at like half speed. But I want to show you something called like a grand substitution, and we observe the idea of a proof there as well. But anyways, this is the end of the video that supports the booklet on applications of functions. Take care, guys. See you later.